So what we can go ahead is now go down to our second method. Again, we've defined an app external to say that it's a public API method, and then we only want the creator of the auction to be able to call it. And then we go into our start auction function. So what we're doing here is a function called start auction. We're specifying three input arguments. First of which is a starting price, which is going to be UN64. It's going to be amount in micro algos to how much the auction should start for. And then our length, which is going to be a timestamp in seconds. And we'll be going over how that works as we go into our logic. Then finally, an asset transfer transaction. Now, you might be wondering, what does it really mean, right? It's pretty self-explanatory when we say we have two integers as our arguments. That just means when we call the method, these two integers will be the arguments to the method call. However, what this asset transfer transaction really means is that when we call start auction, we don't need to pass in anything extra for this argument. Instead, we just need to make sure that the the transaction that comes before our start auction call is the asset transfer transaction. So start auction expects two arguments when we call it, and then it also expects a atomic asset transfer along with it. And this asset transfer is going to be the transaction that transfers the asset from the auctioneer to the auction contract. So it's the transaction that locks the asset in the contract until the auction is over. So let's go and take a look down at our expressions in our logic. First thing we're doing again is verifying our state. We're making sure that the auction end hasn't already been set because we only want to set it once, and we're doing that later in this method. Again, much like before, we're making sure that it's still the default value and that this hasn't already been set. And then another common pattern is doing some input validation. So we're asserting that our asset transfer, the person receiving our asset transfer, is our global current application address. And what we want to do, and I just realized I also forgot to put in one more assertion. So we verified our state, and now we want to verify our inputs. So the first thing we're doing is verifying that our receiver, the person receiving the asset, is actually, or the account receiving the asset, is actually our current application address. And then we want to verify that the asset being transferred, so the expert asset, is equal to app.state.asa. And so this is basically making sure that this asset transfer function is transferring our desired asset to our application. Now, it's important we do these checks because if we didn't have these checks and we just specified that there should be some asset transfer transaction, this could be an asset transfer transaction to a different contract. It could be an opt-in transaction. It could be anything. So we have to manually assert that it is what we expect it to be. In our case, making sure that the receiver and expert asset is equal to what we expect. So in our case, the receiver is our app and the transfer asset is what we have saved in state. And now finally, we can go ahead and set up our global state. So first thing we're doing is specifying our ASA amount. So this is how much of the asset we're auctioning. And we're going to set it to expert.get. So we're getting our transaction and then getting the asset amount. So getting how much was transferred and saving that in global state. And then we want to calculate when our auction should end. So one of our inputs was length, which is how long in seconds the auction for last. And in order to help calculate when the end should be, we call this global.latest timestamp function. And what this will do is we'll get the latest timestamp of the last block in the network. So let's say that this transaction is currently being evaluated on block 2. What this will do is get the timestamp of when block 1 was added to the network. And that timestamp is in seconds. It's a Unix timestamp. So in other words, epoch time. But the important thing to really remember here is that this is the timestamp of the latest block, not the timestamp of current evaluation. So on Algorand, blocks happen every 3.5 seconds. So timestamps will roughly be 3.5 seconds apart. And I say roughly because you have to remember this is a distributed network. There might be some clock skew on individual nodes, or if the network has to catch up, the timestamp might be a little bit off. So always remember that this gets you seconds in epoch time or Unix time, but it's not completely precise down to the second. It might be slightly imprecise or slightly inaccurate, I should say, because it might be some clock skew or some other thing that changes it. So if you need timing down to the precise second, then this is not how you do it. You might need to use something like a time oracle or something that has a constant timestamp. But in our case, in our auction, it's okay if our auction ends a couple of seconds before we want it to or a couple of seconds after. Because the important thing is that's the same for everyone, right? So global timestamp plus our length that we pass in will give us the end of our time. And now finally, we have state.isbid.set. And what this is going to do is simply set whatever our starting price is into our highest bid method. So later on, we're going to go over the bid logic. And so we want our first bid to be forced to beat our starting price. Then thereon after the starting price won't be used. But for the initial bid, we want to use the starting price as that starting point for incoming bids to beat. So that's our start auction function. So now at this point, after we call it, we've opted the contract into the asset. Then we've transferred the asset to the contract, and then we started our auction. So now people are able to bid. But before we get into our actual bid logic, we're going to define what we call a subroutine. And a subroutine is essentially a private method. So earlier in our publicly callable methods, we've been decorating it with this app.external decorator to signify that it's a public method that we want to expose in our API. So now instead, this is a method that we're going to use throughout our contract, but we don't want it to be directly callable by our end users or our front end. So instead, we decorate it with this at subroutine type. And this at subroutine takes one argument, and that is the value that it returns or the type of value that it returns. In our case, there is no return value here, so we're just calling it kill type none. And so to map this to more common programming terminology, this is basically saying this is a private method with a void return type. And so now we can go ahead, take a look at our pay method. We're doing two things. We're taking in two arguments, receiver and amount. And both of these are applied to expressions. And what we're doing is using those arguments, building an inner transaction. The transaction type is going to be a payment. It's going to be to the receiver of our specified amount. Our fee will be 0. And because we haven't specified the sender, it'll be coming from our current application address. So now whenever we call pay, what this is basically going to do is going to send a payment from the contract to the receiver of some amount of algo. So now we have that out of the way, our own little private method that we can use in other methods. We can go to app.external def bid. And so this bid function is the core function that end users will be calling when they actually want to place a bid on the contract or on the auction. So we have two arguments here. The first of which is payment. So again, this means that whenever we call bid, that must be atomically grouped with a payment transaction. And then we also pass in our previous bidder, and we'll talk about why we're passing in our previous bidder in just a second. So now let's go ahead and do some of our assertions before we get into our core logic. First, we're verifying our state. We're making sure that the global latest timestamp hasn't been passed, or our auction end has been passed. So we're getting our global latest timestamp and making sure it is less than our auction end value that we have saved in global state. So this is basically saying and assert that the auction hasn't already ended. And then we're going to do some input validation. This payment is basically the actual bid itself, right? So when we call bid, that's just telling the contract that we're sending a bid, but this payment is what actually contains the transfer of algo to signify that bid. So what we want to do is make sure that it's greater than whatever the highest bid was. For the first bid, this will be the starting price. Then for every subsequent bid, it will just be whatever the highest bid is. And then what we're doing here is also making sure that the person sending the bid is the same person calling the bid function. And then much like before, we also need to assert that our payment get sender is equal to, or not the sender, our receiver, that is equal to our global dot current application address. Much like before, we also have to add in this line to verify that we have the receiver of our payment is actually going to our contract address. Okay, so now we've done our assertions, verified our state as we expected, then verified our input. Now what we want to do is verify that if we do have a highest bidder, we want to return that previous bid. So this is our if statement, and what condition we're checking is the highest bidder equal to an empty byte slice or not. If it's an empty byte slice, then we know that this bid call is going to be the first bid because there isn't a highest bidder defined. So if you remember in our start auction function, we explicitly set highest bid to a starting price, but we never specified highest bidder. And that is so we can know down here whether there is a highest bidder or not. So if this is an empty byte string, then we know that it's the starting price and there is no bid to return. However, if there is an address saved here in our highest bidder.get, then we know we have to return that bid to the previous bidder, right? Every time someone new bids, we want the old bid to go back to the previous bidder and they can then make a bigger bid if they so choose. So if there is a previous bidder, we're going to call our pay function. And again, our pay takes in a receiver and an amount. And so we're going to pay our highest bidder of the amount of the highest bid. So basically just sending back that bid to them. Now, if you're writing this for like production, for example, you'd probably want to change this to take a little bit of a fee off the top or something like that. But in our case, this is just an example app. So we're just simply returning however much the exact amount of bid was. And then we're updating our global state, saying highest bid dot set is going to be however much was sent in the payment. And our highest bidder is now the person that sent the payment. You might notice that we've defined this previous bidder argument, but it's not actually used anywhere. So why the heck are we defining it? And the reason why we need to define the previous bidder argument is so that when someone calls the bid function, they tell the AVM what accounts they'll be interacting with. On Algorand, anytime you interact with an account, an asset, or an application, so this is either reading or writing information about that resource, you have to predefine which resources you're interacting with. So in our case, we might be interacting with an address, the highest bidder, because we're sending them a payment. So we need to tell the AVM whenever we call bid, make sure you have this AVI account locked and loaded and ready to go so we can make changes to it on the ledger. If we didn't have our previous bidder set, what would happen is we'd try to send the payment and then the AVM would panic and say, hey, I didn't know that you were going to be sending this person the payment. I can't send this transaction. And that happens because the AVM didn't know that it should load it into memory. If we don't define it here in our argument list, the AVM won't know that when we call bid that it's loading this previous bidder account. So in our case, this previous bidder account has to align with our highest bidder account. Okay, so now we've gone over a bid method and summarize basically if the auction hasn't ended, use the payment attached to make a new bid, pay back the previous person if there was a previous person that bid, and then update our global state to now contain who the highest bidder and what the highest bid is. And so this will be the only function that's called up until global latest timestamp has passed our auction end. So when the auction ends.